All right, so yesterday we talked about our equations for velocity and for acceleration, right? So average velocity and average acceleration. Today I want to talk about using those equations to find other things. So I'm going to start by writing those equations out so that we can look at our situation and figure out which one's going to be helpful. So our velocity equation for average velocity was our change in position over our change in time. You guys remember this? Okay. Then our acceleration equation is our change in velocity over our change in time. Okay. So both of them look fairly similar because they're both over your change in time. But the big difference is for velocity, we're looking at how fast our position is changing. For acceleration, we're looking at how fast our velocity is changing. Good? Okay. Now, there's going to be situations where we have questions like, let's say that our chinchilla, John Chilla, moves, let's say, I don't know, how fast do you want him to go? Anybody? Yeah.
2 miles per hour.
2 miles per hour? Okay, so let's say John Chilla is moving at 2 miles per hour. Okay, let's say he's going in the positive direction. He starts at 0, 0. Okay, how long is he going to move for? Yeah.
35 seconds.
We're going to have to convert if we use seconds. So we could do something like 0.2 hours if you want.
Okay.
That's not 30 seconds, but it's, yeah. So we could do 0.2 hours. Everybody good with that? Okay. All right, so let's say he goes 2 miles per hour for 0.2 hours. Okay? We want to know how far John Chill has gone. Okay? Now, we have a speed or a velocity, and we have a time, right? We're looking for a distance or a change in our position. Are there either of these two equations over here that have those three variables in them? So we're looking for velocity, time, and position. There's one of these that has them in it. Which one? Yeah?
The acceleration.
So does this one have position in it?
No.
No, it doesn't. Okay. Does this one have position in it? Okay. So this one has velocity, which we know. This one has time, which we know, because he moved for 0.2 hours. That's our delta t. What we're asking for is how far he went. So what's our change in position from here to here? Does that make sense? So this equation has all the things that we want in it, but it's not solved for the thing we want to know, right? So what we're going to do is we're going to take this equation and we're actually going to move it around, move the variables around, so that we actually get an equation for what we want, okay? So what we know is that our velocity is 2 miles per hour. Our time, or our delta t, is 0.2 hours, and we want our distance. Sorry, I'm going to be a little bit more technical with this. We actually want our displacement. We want our distance from where we started to where we ended. Okay, so what our displacement actually is, in this case, is going to be our change in position. Okay, so this is delta x. Everybody got this? Yeah? So if we take our equation, we have our equation v equals delta x over delta t. Okay? So we don't want this to equal our velocity. We know that. We don't want it to equal delta t. We know that. We want an equation that says delta x equals something else. Good? So that means we need to get the t not on the same side as our delta x. So what can we do to get the t over to this side? Yeah. Multiply both sides by delta t. Okay, so here the delta t will cancel out. Yeah? And we get delta t times v equals delta x. Good? Any questions on how I got there? You guys need me to close my computer so you can see better? All right, so we've got delta t and v equals delta x. Okay, so now we have an equation that is a general case, right? So we can use this for any situation in the future where we know or we want to know our delta x and we know a velocity and a time. Okay, everybody good? Let's actually put our numbers in now. So we know our v should be 2 miles per hour and our delta t should be 0.2. All right, so what do we get? 0.2 times 2? Yeah.
0.4.
0.4. Okay. What units are we going to have? You guys remember how we check our units? No? All right. We can cancel units out just like we could before, just like if it were numbers. So we can cancel our hours out. What are we left with? Yeah. Miles. So we get 0.4 miles. Let me make sure this is, yeah. Okay, so we get 0.4 miles. So in these this 0.2 hours, our chinchilla will have gone 0.4 miles. Good? Any questions? No? Okay. So this is a very common thing that you would do. Okay? Now, we can also take this equation and say, let's say we know that our chinchilla is going to be going. Let's use meters per second this time so we can get a little bit more reasonable of the time. Let's say that we know our chinchilla likes to go 2 meters per second. Okay? But our chinchilla doesn't like to go 2 meters per second for very long. So maybe our chinchilla only likes to go 2 meters per second for 5 seconds. Okay? Actually, that's not what I want. That was the same problem as, or similar problem to what we did before. So I'm actually going to give you a distance this time. No. Yes, that is what I'm going to do. Okay? So I'm going to give you a distance this time. Okay? So we know our chinchilla likes to go 2 meters per second. Let's say that from one side of his cage to the other cage, let's say he's got a nice big cage, is 2 meters. Okay? 2 meters is a pretty good size cage. So, okay? Our question this time is going to be, how long does it take the chinchilla to go these 2 meters? Okay? You can probably look at it and tell me this 2 meters per second. You're going 2 meters. Should be easy. But let's actually look at how we get the equation in the right form. So this time we're looking for how long did it take? I think we should have a calculator. So which variable is going to be our how long did it take? Okay, yeah. It's going to be our t. So this one is delta t. This is the one that we're looking for. Okay? This is going to be our velocity. So we know our velocity. This is going to be our change in position, or our delta x. Everybody see why those are those things? Good? Okay. So we're going to start back with our equation. We have v equals delta x over delta t. This time, we want something that says delta t equals this. So we want to get delta t by itself. What's the first thing we should do? Any ideas? Yeah. Actually, so that's a good thing that you brought this up. We could put the v and the x in there, okay? But once we're done solving it, we will only have an equation for this specific case. If we don't put our v and our x until the end, we'll actually have an equation that we can use every time we need to find delta t, okay? So we will get the correct answer if we put our v and our x in right now, but then we can't use it again later. Cool? So that's why physicists like to solve things in variables, because we can actually get an equation we can use later, and we can also get other information from those equations that we get. Okay? We'll get to that later on. All right. We are actually going to start this just like we did the other one. Okay? If you're dealing with equations like this, the first thing you always want to do is get whatever's in the denominator out of the denominator. Okay? Always a good tip to start with. So we're going to multiply both sides by delta t. Okay? So delta t is going to cross out on that side. We get the same thing that we got last time. But we can't stop here. Last time we were looking for delta x, it was fine. This time we're looking for delta t. We still need to get it by itself. How can we get the v to the other side? Anybody? Yeah. Yep. Divide both sides by v. Our v will cancel out on this side. We get delta t equals delta x over our velocity. Okay? Now, you remember how we checked our units on the last time? Yeah? That is always good practice. So if you keep your units with your numbers, then you can always double check, make sure that you get units of time. So in this case, we would be looking for units of seconds. So let's see if we actually get units of seconds. So let's put our numbers in. Our delta x is 2 meters. Our v, not delta v, our v is 2 meters per second. Okay? All right. So we've got 2 divided by 2. We are going to get 1, which is good. That's what we thought we were going to get. And now, if we look at our units, the easiest way to see how this works is to remember that a fraction in the denominator, okay, so dividing by a fraction like this, is actually the same as multiplying by it upside down. Okay, so if we write this upside down, we've got our meters from the numerator times our upside down fraction down here. So we have seconds over meters. Good? We're going to cancel these out, and we do, in fact, get seconds, which is exactly what we were hoping we'd get. Good? So I would, especially if this is a test or something like that, which hopefully we will have one, I'm thinking probably next week. I don't want to give you a test on Halloween or on our costume day. So we will find that this is probably one of the easiest and fastest ways to make sure that your equation is right. Okay, because it's real easy to accidentally divide one side by v and accidentally multiply this side by v, or write it down wrong, or something like that. Okay? This is by far going to be your fastest way to double check that you've done it right. Good? All right. 9 times out of 10, if you get the correct units here, you've done the problem right. Okay? It's not a complete 100% guarantee, but it is a pretty good indication you're on the right track. Are there any questions? No? Okay. Cool. So, we've gone over the 2 possible forms for our average velocity one. Now, we want to go to our acceleration one. Okay, so we're going to be dealing with that equation. Just so that you guys have a quick reference, we've solved for delta x, which is v delta t, and we've solved for delta t, which is, let me make sure I write it down right, delta x over v. Good? So those are our 3 forms of this equation. One thing I do want to make clear, these are still the same equation. We've just moved the variables around. Okay? All right. So let's do stuff with our acceleration one. Actually, how much time do we have left? So I want to make sure I give you guys your, oh, we've got plenty of time. All right. So back to John Chilla. All right. We are going to deal with our acceleration one, like I said. For the first one, let's find our final velocity. Okay. So let's say we happen to know that John Chilla can have an acceleration this way of, I don't know, let's say it's really fast and accelerating. Let's say 12 meters per second squared. That's a pretty big acceleration, okay? That's actually larger than the acceleration of gravity. So, fun fact. So, John Chilla is really fast, okay? But let's say that he can only keep that acceleration up for a really short amount of time, okay? So, let's say he accelerates for, I don't know, 0.3 seconds. Okay? We want to know how fast is John Chilla going after these 0.3 seconds. Okay? So which variable are we looking for here? Anybody? Yeah. We're looking for our speed. So we're going to be looking for velocity here. Okay? If we want to get really technical, this is our final velocity. Okay? Which we did kind of talk about how we can take our delta V and make it final minus initial. Yeah? Here, we're starting from 0. But I will actually write this out in the equation just so that we can kind of keep track of how we do all the math. Okay? This is going to be our delta T, and this is our A. Good? Okay. So our equation is A equals V, delta V over delta T. Okay? Everybody good? Okay. We're going to start by expanding the V into our V final minus V initial, because there's a few things I want to talk about in regards to how we do the math. Okay? So our V final minus our V initial is in the numerator, right? We are looking to get V final by itself. Okay? Good? What's our first thing we should do? What was the thing I said was always a good idea, the first thing to do in the last problem? Yeah.
Is that the denominator?
Yeah, so get rid of the stuff in the denominator. So what we want to do is multiply both sides by t. So we got delta t canceling out over here. We need to multiply it by over here. So we get a delta t equals v final minus v initial. Okay? So we want to move v initial to the other side. How do we do that?
Add it to both sides.
We need to add it to both sides. Something to watch out for. It's real easy, especially if you're going fast and you just did this step. It's really easy to say, oh, I need to multiply by a negative initial velocity. Don't do that. Okay, that's not right. You need to add it to both sides. Okay? All right, so we get a delta t plus our initial velocity equals our final velocity. Good? Any questions? Yeah? No, we're good? All right. So we have now solved for v final. Okay, in this case, if we had just solved for delta v, we would have gotten the same thing because our v initial is going to be 0. Okay? There are going to be times where sometimes you want to know our change in velocity. How much did our velocity change? And in that case, we would solve for delta v. Good? All right. So let's put our numbers in. Our acceleration is 12 meters per second squared. We've got 0.3 as our time. And then we add 0 meters per second as our initial velocity. Good? Any questions? All right, what do we get? Yeah.
0.36 meters per second.
So actually one of our seconds is going to cancel out. Okay. This should be very similar to a third of 12. Because 0.333 repeating is a third. So what do we get? Yeah.
3.6.
What was it?
3.6.
3.6? Did you say, it sounded like you said 0.36.
I said 0.36.
All right. Cool. And because our seconds will cancel out here, we get meters per second, which is good because that's our units for velocity. Yeah? Any questions on this one? No? Are you guys able to follow what we're doing here? Most of you should have at least done this in math class a few times. Yeah? Maybe mostly with numbers, not with variables. It's the same rules. Okay? Any questions? All right. We've got one more to solve for then. We'll put this one over here. All right, so this time we're going to be looking for our delta t. I'm not going to do the final minus initial thing because most of the time we're looking for how long do we want this acceleration to get to this velocity. Okay, so let's say our chinchilla is going a little bit slower now. Let's say that he's got a velocity of, or an acceleration, sorry, of 1 meter per second squared. So he's definitely not at his max acceleration. But we want to know how long it'll take him to get to a acceleration of, I don't know. Oops, not acceleration. Velocity. Let's say let's say 12 meters per second. Okay? So our variable, since it says how long, the one that we're going to be looking for is going to be our delta t. Okay? What's this guy here? Anybody?
Velocity.
Close. Got a second squared. That makes a difference.
Oh, acceleration.
Acceleration. So that's our acceleration. And this one is, this one's not squared.
Velocity.
This one's velocity. That's one easy way to tell the difference to see if it's velocity or acceleration. If it's got the seconds squared, it's acceleration. If there's just 1 second, it's velocity. Okay, so that's one quick way to tell which one's which. All right. So this is going to be our delta V actually, because we're going from a velocity of 0 and we're reaching a velocity of 12. Good? Okay. So our equation is A equals delta V over delta T. So this is going to be very, very similar to when we solved for our delta T here. Okay? So what was the first thing we did to get our delta T?
Multiply delta t by both sides.
Yep, we want to get it out of the denominator, so we're going to multiply it by both sides. So we get A delta T equals delta V. Now what do we do? Anybody? How do we get the A to the other side?
Divide.
You divide both sides by A. A cancels out. We get delta T is delta V divided by our acceleration. We'll put our numbers in. So our V goes on top. We get 12 meters per second. Our acceleration goes on the bottom. So that's 1 meter per second squared. Okay? 12 divided by 1 is just 12. Okay? Then we're going to do the same thing with our units. Okay? So we have our units on the top, which will stay the same. We're going to flip the ones on the bottom and multiply by it. So we get seconds squared over meters. Our meters cancel out, and one of our seconds cancels out. So we end up with 12 seconds, which is good because we're looking for time. Everybody good? You guys have any questions? No? All right. This sort of technique here is really, really useful in physics. Okay? This means that instead of having to memorize these 6 equations over here, or 3 forms of these 2 equations, you just have to memorize 2 equations, or just have to know 2 equations. Okay? And that can make a big difference, especially when there are a lot of equations in physics. Okay? Make sense? All right. One thing I would recommend, especially if you guys don't like word problems, which most people tend to not like word problems, physics is pretty well all word problems because it's all real life applications. Okay? So if you go through your problem, and as you go through your problem, you say, oh, hey, this has units of meters per second squared. This thing's an acceleration. And you say, and you like maybe do like what I did here and say, A is this thing. Okay? Or as you go through, maybe this is your velocity. Okay? So you see something with meters per second on it. Maybe you have two velocities. Maybe you have a starting and final velocity. Okay? Go through and label those with the variables that you know go with them. Okay? Physics equations use the same variables for each thing. Okay? So no matter what equation you're going to use, A is always going to stand for acceleration. So if you go through and label them like that, one, that can help you figure out which equation you want to use. And two, that means that when you're trying to put your numbers in, you know what numbers go where. Good? All right, any questions? No? All right, I'm going to stop the live stream now, and then I'm going to pass out the worksheet and talk about that a little.